Hello everyone and welcome back. In the previous video, we already calculated the torsional stress caused during tightening. But here is the real question. After applying the actual load from our ANSYS simulation, are these M8 bolts still safe according to VDI 2230 guidelines? In this video, we are going to answer exactly that question. So, this is the same bolted connection that we have been using throughout this series. It consists of two steel plates connected with 4 M8 bolt with a strength class of 8.8. Each bolt was preloaded with 18.6 kilonewton, and I did initiate actually another simulation but without bolt pretension in order just to get only the external forces like acting on each bolt. And as you can see, I will go to the other simulations. I already suppressed the bolt pretensions, and under the same load, the 20 kilonewton load upward on these plates, I got actually around 8,335 newton as axial force, external axial force, which is act on these bolts. And now we will use the VDI 2230 to determine the maximum force acting inside the bolt and finally check whether the bolt is safe against yielding or not. In order to do this check, actually we need to fill this table. So I already prepared this table for you and with needed formulas. So what we are gonna to calculate in this video actually is the maximum bolt tensile load, which is called the FS max. In order to calculate these parameters, all what we need is to know the bolt pretension, and this is already known to us. As I mentioned before, for our bolts we are using 18.6 kilonewton. In case you have in your model or other application like another bolt size or strength class, you can check my previous videos. Also, I already mentions a table that show the bolt pretension for all bolt kinds and size and strength class, so you can check it. So in addition to the bolt pretensions, we have to add a load factor phi multiplied with a FA, which is the external applied axial separation force, which is in our model. Here I did it without bolt pretension to get this external force, so the FA, and in my case it's 8,335. So the bolt pretension that we used on our model is 18.6 kilonewton or 18,600 newton. The external force or load that we have, the FA from this simulation, is 335 newton. And now in order to calculate the load factor phi, we need to know actually two important parameters, which they are the bolt stiffness and the plate stiffness. In this video, actually, I'm not deriving these stiffness values in detail because that calculation deserves its own dedicated video. So for now, we will use them to determine the load factor. So in our case, the bolt stiffness, it's around 538,000 kilonewton per millimeter, and we have this value as the plate stiffness. So in order to calculate the phi factor, we have to use this formula, which is not more than the bolt stiffness divided by the bolt stiffness in addition to the plate stiffness. Based on this formula, we got the following load factor phi, which is around 0.182. That's mean 18.2% of this external force will become or go to the bolt actually to us, and the rest they will be as a clamping force or on the plate connection. So the bolt will not take the overall 8,000, he will got just a part of it, exactly 18%. So after applying the our general formula, which is in order to calculate the FS max, so after calculating the bolt pretension in addition to the load factor phi multiplied by the external load that we have, we got an overall force of 20,100 16 Newton. And this is the force that we have to use in order to calculate further the stresses acting on the bolt. So I'm gonna back actually to the previous table that we did use to calculate the torsional stress. If you didn't see that, you can like see the previous video. Our goal in the previous video was to calculate the stresses on the bolt taking into consideration the torsional stress due to tightening. So based on that calculations, we came to an overall stress or equivalent stress on the bolt of 595 megapascal, but that just without having any external load on the model, just taking into consideration the bolt pretension and the tightening. So now that difference and what we calculate actually in this video is what happens when we have a load of 20 kilonewton in our model. So on the middle, if we have the 20 kilonewton and this will be distributed on the 4 bolts and so on, how are these like bolts still safe according to VDI? So let's check this together. So now we did calculate the FS max from this table, which was like that 20,116 Newton. And from this FS max, actually now I have to calculate the stress. So before we just like used the bolt pretension divided by the stress area and we got the 508. Now we have to divide this value by the stress area and we will got actually this value, which is like 500, around 550 megapascal. Before we had like 508, so we have like almost like around 40 megapascal like extra that coming actually through these like 20 kilonewton load that we have in our model as an extra stresses on our bolts. But this is like not everything. Here we still have to take into consideration the torsional stress due to tightening. So in order to do that, we have to use this formula to calculate the equivalent stress, taking into consideration the axial stress from preload and the external load together, combined, which is this value, with the torsional stress above the 207 megapascal. Of course, here in this model, we use 90% of the permissible like bolt pretension, which was the 18.6, and that's why we got like 207 as torsional stress. In case you use like lower value of preload, so we are expecting to have lower stress from torsional stress and an overall lower stress. So now we did calculate everything with a 90% of the permissible like bolt pretension for the M8 bolts, and we got finally, after like inputting this value and the torsional stress in this equation, we got the final stress acting on the bolt under the load of 20 kilonewton on our design, which is like 631 megapascal. Actually, it's like a little bit high. So as you already know, we use like 8.8 strength class for these bolts, M8 bolts, and these bolts have a yield strength of around 640 megapascal. And you can see like clearly that we are like nearly like almost near to the yield strength of the materials. And based off that, dividing our yield strength of the bolt by our value, we got like a safety factor of about 1.013, so it's almost 1. So it's not like perfectly like recommended, like according to VDI. VDI actually recommend to have always like a safety factor like above 1.1 for like safe bolt plate connections in that case. So in this video, we verified that our bolt like theoretically does not like yield under the combined effect of preload, external loading and tightening torque, but it's like recommended to use like a better bolt size, like bigger bolt size instead of M8 like M10 bolt, or the same bolt size with like higher strength class. It could be like also like a solution. But that's the only half of the design. So in the next video, we will calculate the remaining clamping force in the joint and check the safety factor against the slipping. So according to all the videos we did like posted earlier and this video. And with the next video you will be able to have all the safety factors like against yielding, like shearing, like slipping, and so on. So on the next video we will like learn how to get the safety factor against slipping and knowing the remaining clamping force on that joint, which is like often the governing design criterion for bolt joints. So if you are following this VDI 2230 series, make sure to subscribe so you don't miss the next part.